Good morning, everybody, and thank you for the introduction. My name is Aamer. I'm from the NVIDIA Architecture Research Group. Today I'll be talking with my research hat on. So I will not be announcing any products. I will not be talking about anything NVIDIA confidential internal, right? Today we're going to be talking about data disturbance errors, such as RowHammer, which have been troubling the DRAM industry for over a decade now. I will present some security-first DRAM design that we will need to not only cope with the data disturbance errors of today, but also tomorrow, okay? So quick background, DRAM technology scaling has enabled memory vendors to increase memory capacity by packing cells close to each other, right? Unfortunately, as we all know, as you pack these DRAM scales closer to each other, they're causing inter-cell interference, and this causes DRAM cells in one DRAM row to disturb DRAM state in another row, which we are calling data disturbance errors. So RowHammer and RowPress are two well-known techniques or modalities that have incurred data disturbance errors in neighboring victim rows, either by repeatedly accessing a row or keeping a page open for a long period of time. These are not the only modes of data disturbance errors. We'll talk about a few that have been released towards the end. But these data disturbance errors are not only a reliability problem, but a security problem, right? And they have been shown to escalate privileges on modern systems. Thus, we need low-cost, scalable, and generalizable solutions that can tackle the data disturbance rates of today, modes of today, and tomorrow. Okay? So let's take a deep dive into RowHammer for a moment, and then we'll talk about RowPress later. So RowHammer is a phenomenon where frequent activations to DRAM rows cause bit flips in neighboring rows, right? The frequently accessed rows are called aggressor rows, and the victim row and the row that has the bit flips is called the victim row. The RowHammer threshold, which is the number of RowHammer threshold, which is the number of activations it causes to cause bit flips in the neighboring rows, has been decreasing over time. Memory vendors have attempted to address this problem directly within DRAM with a two-part solution, right? First, they introduced an in-DRAM tracker, which is a buffer to track aggressor rows. And second, they periodically mitigate these victim rows and potentially neighboring rows, which is called the blast radius, to avoid the bit flips in those victim rows. To better understand victim mitigation, let's take a quick crash course in DRAM refresh. So as we know, DRAM is a volatile device. It must be refreshed periodically. So the DRAM refresh period is divided into 8K refresh intervals, which are called TREF-E. A small fraction of each refresh interval is dedicated to refresh the different rows in the DRAM. And the remainder time is available for normal DRAM accesses. And for a given parameters of the DRAM timing, let's assume for the study that we're doing, there are roughly about 79 activations. Okay? So to perform RowHammer mitigation, what you end up doing is that you take some time of this TRFC and borrow that and consult the tracker, in DRAM tracker, and mitigate the victim rows. So RowHammer mitigations are basically issued by borrowing some time from refresh. Okay, so now that we understand how in-DRAM trackers work and how mitigation is work, let's look at the landscape of in-DRAM RowHammer solutions to date, right? We've got high security solutions such as ProTRR and Mithril that are out there that requires hundreds to thousands of counters. And so they have high storage. Then we have in-DRAM mechanisms that people have broken so far, which is TRR, something like DSAC and PAT. They require less than 16 counters per DRAM bank, but they have very low security. Our goal is basically to design a low storage in-DRAM tracker that has high security. So that's what we're going to try to do. So to understand why existing low-cost DRAM trackers fail, let's first we introduced a taxonomy for how tracker management policies work. First, you have an insertion policy, right, that inserts lines into a tracker, or addresses into a tracker. You have an eviction policy. These trackers are finite bound, so you must evict something if something's not in there. So you have an eviction policy. And then you have a mitigation policy to choose a row from address row from the tracker and mitigate it. These three policies have three modes of failures. First, if you don't insert a row address into the tracker, it will not be mitigated. So that's the source of what we call as tracker insertion failure. If you insert a row into the tracker, but then you discard it before you actually mitigate it, that's your second form of failure, which is called tracker retention failure. Failure from discarding the address. Third, mitigations only happen at TRFC, right, during the refresh period. So we insert the address into the tracker, but we don't mitigate it until the later time during refresh. So by delaying the mitigation, by being tardy, that can also cause failures. So with these three policies in mind and with these three failure modes in mind, let's see why existing in-DRAM trackers fail. Existing in-DRAM trackers, DRAM vendors were like, oh, look, the reason why trackers fail today, or why RowHammer happens is that there's a row that's frequently accessed, right? So they said, oh, let's keep track of frequently accessed rows. So they built a tracker, right? It's a counter-based tracker, right? It has addresses and counters within it. You always insert into the tracker. If you get a hit in there, you increment the counter. If you miss, you evict the least frequently used line. And then when it's time for mitigation, you consult this tracker to find the line, the address that has a high counter value, and you mitigate that, right? The problem is that this was an ad hoc mechanism that vendors decided to use. They didn't even think about principles, principled approach. So this tracker is an access-dependent tracker, right? Carefully crafted patterns like trespass or blacksmith access patterns found out that, hey, if we can overwhelm this tracker with an access pattern that is much larger than the tracker size, we suddenly start causing addresses to be evicted, and you start seeing tracker retention failures. So the goal of our work is how can we go about this, designing an access pattern independent tracker with bounded failure rate. So let's take a security first approach. So let's do one thing. Let's get rid of the counters. So let's just store addresses within the tracker. Okay, so to this, let's go towards an address independent tracker. One potential tracker policy is design it as a FIFO. FIFO has some very good security principles that we can exploit. So with a FIFO tracker, you always insert into the tracker no matter what, right? So all accesses get inserted. When the tracker is full, we'll evict from the head. And then when we want to mitigate, we'll always take the first guy, right? So that's the FIFO tracker. Now, I'm going to represent the FIFO tracker this way. We're not evicting from the middle, right? So there's a problem, though. With a FIFO tracker, if your access pattern is larger than the tracker size, such as thrashing access patterns like trespass, you will start getting retention failures, right? So how can we address this? It's well known in the caching industry that if you're going to be thrashing, probabilistically insert some of the addresses in there so you get some of them to fit rather than none, right? So we're going to take a probabilistic approach. By doing a probabilistic approach, what we're going to do is we're going to sample the addresses and insert them into the tracker. So now the question is, what should be our probability for insertion? If we use a very high probability of insertion, we'll be causing retention failures. If we have a too low insertion policy, we'll probably be getting tracker insertion failures. What should this probability be? Okay, so let's go back to how refresh works, right? The way that mitigation refresh works is that at the end in your TRFC window, you're choosing an entry from your tracker, and mitigating it. So your mitigation rate is once every however many activations are possible in your TREF-E window. So in our example, it's a mitigation occurs roughly 1 every 79 activations. So using that observation, the insight is the following. Your tracker insertion rate must match your mitigation rate. By doing this, we will not overwhelm the tracker, and we'll hopefully not have too many retention failures or insertion failures. So that's the policy that we're going to use. So there you have it. Now we have a tracker that has probabilistic insertion, fairly simple, right? And we can now start bounding the failure rate. So let's assume that we have a mean time to failure of 10,000 years, which is equivalent to the DRAM fit rate. So using that, if we have a probability of insertion of P, right? And let's assume for a moment that everything that you insert is going to get mitigated. What's your probability of failure? Your probability of failure is from not inserting the address into the tracker. The probability of failure is 1 minus P raised to the RowHammer threshold that you would be having. And if that's your mean time to failure, you can actually compute TRH, the RowHammer threshold, to be 1530. So now we actually have a approach with probabilistic insertion that your RowHammer threshold of 1530, which is lower than the RowHammer thresholds that are of DRAM technologies out there today. Okay, but we all know, right? The tracker is of bounded size, right? Something has to get evicted, right? So if we're going to evict something, the tracker has a loss probability, right? So if you have a loss probability L, right, what is your effective mitigation rate? It is basically the probability P of insertion times the survival probability, which is 1 minus L, loss probability. So now we can analytically bound the loss probability of a FIFO tracker, assuming a 16-entry tracker, right? You now have a mean time to failure of, you can bound the RowHammer threshold. With a 16-entry FIFO, you actually have a 1575 RowHammer threshold, okay? Now, but like I said, after you insert it, there's another mode of failure, right? That's tardiness. This is the failure from delaying the mitigation. So how do we quantify this, right? Recall that in-DRAM trackers actually, after you insert something into the tracker, you actually have to wait till the refresh time, right? So if you're going to wait till the refresh time, let's bound how many possible activations are possible, right? If you have a 1-entry tracker, you insert at the very beginning, you can have up to W possible activations, right? So your tardiness is up to W. Let's generalize this. If you have an N-entry FIFO, right? The first guy will get mitigated in the first TREF-E, but the green guy will wait up till N times W activations, right? So for an N-entry tracker, right, so we can bound what the tardiness is. A 1-entry tracker will have a tardiness of 79, but a 16-entry tracker will have a tardiness of 1264. So now we can bound your RowHammer threshold by taking the threshold that we got from tracking for insertion and retention failures and add on the tardiness. And when we do that, actually, you'll end up seeing that if you have a very large tracker, you're going to be hurt by tardiness, right? So large trackers are really not a good thing, right? It turns out that a 4-entry tracker works best. So with this, you now can support a RowHammer threshold of 1900. So there you have it, right? This is a design that we call Pride, which we presented at ISCA, right? Where this is the first secure, low-cost in-DRAM tracker with bounded failure rate. We can support with 0 performance overhead, if we just did 1 mitigation per TREF-E, and support a RowHammer threshold of 1900 with 0 performance overhead. We can scale up the mitigation rate by using DRAM's RFM feature, by increasing the refresh frequency. If you increase the refresh frequency, your probability increases. So let's say that we issue mitigations every 16 activations. Your probability goes from 1 over 79 to 1 over 16. This does incur a performance overhead of roughly 1.6%, but now you can actually support a RowHammer threshold of 500, of 400, right? Okay, so great. Now we've got a scalable mechanism that allows us, and a low-cost mechanism that can support RowHammer thresholds of today, of below today, and to ultra-low 400. But there are some possible enhancements, right? There's a limitation of pride, right? One of the problems with pride is that for each activation where it's selected independently with identical probability. So every row address or activation, we're going to toss a coin and say, hey, can I select this? If you do this for each one of them, there's actually a problem. Sometimes, actually 37% of the time, you will not choose a row for mitigation, right? So the probability of non-selection is 37%. How can we go about addressing this? The way that you can address this is rather than actually tossing a coin on each activation and say, should I select this? Should I select this? Should I select it? Why don't we just do uniform sampling, right? At the very beginning of the TREF-E interval, throw a random number between 0 and 78. And that's the future entry with which we will mitigate. So your insertion rate into your tracker is actually similar to what we're doing with pride, but rather than suffering the non-selection problem, we're going to be able to have 0, right? This problem is not going to be there, right? So how do we go doing this? This is something that we presented at Micro, where what we'll do is at the very beginning of the ref interval, we'll throw a random number, right? And we'll store it into a register called SAN, or which is the selected activation number. And then each time we get an activation, we'll have a counter that increments up. When the activation counter matches what we had selected as the random activation to choose, we'll store that address into a register called the selected activation register. And then we'll keep on going. When we get to the end of the TREF-E and we're going to refresh, we'll consult the register. If there's an address in there, we'll go ahead and mitigate that. This approach requires only one counter now, as opposed to the 4 counters of pride, right? So now Mint actually has 25% lower threshold than pride. It beats a 4-entry tracker. Again, has 0% performance overhead, right? And when we scale it with RFM, we can actually get reach a RowHammer threshold of 350. Okay, so there you have it, right? We've done this work to go about taking a security-first approach and designing a low-cost tracker about the same size or lower than TRR that is in products and get high security. Okay, so we've been doing all of this work, and around this time that we had presented or wrote up Mint, JEDEC was sick and tired of all of these RowHammer trackers getting broken. So a new standard has been introduced, right? This is the per row access counters, where DRAM is now going to be having dedicated in-DRAM storage and a timing budget, right? So this technology PRAC is optional in DDR5, but it's going to be mandated in DDR6, LPDDR6, and most likely in HBM5 too. So how does PRAC work? Requires changes to the existing DRAM design, where you take the existing DRAM design and you add some more state within it, which is the activation counter per row, right? Which is the tracking structure. These counters are basically going to hold the number of times a row is activated. So we've got some logic. Whenever a row is activated, we're going to increment a counter. So that gives you the tracking structure. So when do you go about mitigating? So when the counter reaches a given mitigation threshold, at that point, the PRAC logic will insert this into a service queue, okay? When that service queue fills up, the memory is going to send an alert backoff signal to the DRAM, to the memory controller saying, hey, I think I'm having issues, right? Data disturbance error potentials over here. stop issuing request, send me a mitigation request. A mitigation request is issued using RFM. And when the RFM arrives, it's going to consult this service queue, and you go ahead and check, get the entries from the service queue and mitigate it. So PRAC is and the ABO is a principled framework that helps protect against RowHammer. But guess what? The implementation of PRAC is deferred to the DRAM vendor. Okay? So one crucial component of PRAC is the service queue. How should the service queue be designed? Should it be FIFO? Should it be LRU? Should it be LFU? What should it be, right? So again, if DRAM vendors decide to take an ad hoc approach and say, oh, Pride said, let's do FIFO. All right? So what if you did a FIFO-based service queue? Pride said, let's not use access counters in the tracker. Let's use FIFO. So let's say we decide to use FIFO. The problem is if you use a FIFO queue and the service queue becomes full, then the activations that occur during an alert and before an alert can actually render PRAC entirely insecure. So instead, what you actually need is you need a counter-based priority queue, right? So this is some work that we talked about at HPCA called QPRAC. And if you implement it with a priority queue, you actually can get RowHammer thresholds of less than 100 and less than 1%. So what I basically wanted to bring up over here is that even principled frameworks, right, you still need to design them carefully to ensure security. You can't just use ad hoc mechanisms and say, oh, look, FIFO, let's go about doing that. You must take a principled approach. Okay, let's switch gears for a minute. Let's talk about RowPress, right? So recall, RowPress incurs bit flips when you keep rows open for a long period of time, okay? The biggest problem with RowPress is that it flips bits with fewer row activations, okay? So which row activation count is what we've been calling the RowHammer threshold. So thus, with RowPress, with fewer activations, the longer you keep a row open, the effective RowHammer threshold actually drops. So with fewer bit flips, you now, with fewer activations, now you basically are breaking existing RowHammer trackers. To address this problem, right, existing proposals suggest limiting the amount of time that you should keep the row open, right? When you keep the row, limited time row is kept open, you have to tolerate a lower RowHammer threshold, but it has problems. First, it requires changes to the DRAM standard, right? You now need to design your RowHammer trackers to tolerate a low RowHammer threshold, right? And again, it's not a generalizable solution, right? I mean, you have to design a point case solution for RowPress. The question that we're asking is, can we generalize the RowPress problem and use existing RowHammer mechanisms to address RowPress? So what we do is we actually suggest that to address this, the key idea over here is, why don't we treat the row open time as an activation? If we can treat the row open time as an activation, then we can convert row open time to equivalent activations that occur within DRAM. The way that we can do this directly within DRAM is that in the DRAM, when a row is opened, we start a timer. When the row is closed, we stop the timer. We take that time and divide it by TRC, which is the activation time, and that effectively becomes your effective activation count, and use this in a precise manner with existing RowHammer mechanisms. So let's convert RowPress to a RowHammer problem. So let's take the example of Mint to do this. What we can do is keep Mint design as is, right? If a row is activated, again, choose your activation number as before, that we probabilistically randomly sample. For the first activation, you increment the counter, right? If you opened up a row and you kept it open, rather than incrementing by 1, you're actually incrementing by some value, right, which is the ratio of the open time divided by the activation time, which is now 1.5. Let's say the next row was also opened and kept open for a little time. Now it becomes, the value is 2.8. This value is greater than your selected activation count. So you sample that in and voila, right? I mean, so now what you've done is you've converted RowPress into RowHammer. And this concept of Impress, which was presented at Micro last year, generalizes RowHammer mechanisms to also handle RowPress. You can incorporate this in Mint, you can incorporate it in QPRAC, and so on. Okay? So the next thing that I'll quickly talk about is the role of ECC in mitigating data disturbance errors, right? Memory controllers use system-level ECC for integrity, right? It protects data in flight, gives you end-to-end protection. You have mechanisms like SecDat and TechDat to do so. Memory vendors are also supporting on-die-ECC for in-DRAM integrity, right? I mean, it's transparent to what the memory controller does. I mean, the error correction happens on DRAM and then it's sent over. So system-level ECC and on-die-level ECC can protect against DDEs as well. I mean, I know there are papers out there that have talked about how you can break system-level ECC, on-die ECC, but they also do play a role in addressing data disturbance errors, which typically are single bit. So to now sort of put my NVIDIA hat on for a moment, right? The NVIDIA strategy for mitigating against data disturbance errors is to leverage memory vendor solutions, right? We've got in-DRAM trackers, we've got PRAC coming, right? We've got on-die ECC, right? Memory controllers, they're designed to spec, right? We have memory controller solutions such as system-level ECC. We've got system-level solutions such as multi-instance GPU that gives you isolation. It addresses security, it doesn't address reliability, right? But it is an approach. And as the person with the research hat on, we've been engaging memory vendors with novel research in securing in-DRAM trackers through something like Pride or Mint or through secure per-row access counters, with QPRAC, which the next speaker will talk a little bit more about in detail. So, speaking of the next note, the next talk, which is about GPU hammer, right? I mean, talks about how we can actually break GPUs with RowHammer. So, a quick point over here is it's not NVIDIA products alone are susceptible to RowHammer. All products that are using DRAM are susceptible to RowHammer. NVIDIA products have mitigation in place, right? I mean, we've got system-level ECC. It's default on in certain products. Other products we need to do enabling. On-die ECC is also available in select systems. And the GPU hammer work actually does show, right, that system-level ECC protects against RowHammer. So, from a consumer-grade systems that are out there, they do not support graphics systems. They do not support ECC, right? So if you do require enhanced integrity, we should switch to professional data center NVIDIA parts. And let's ensure that ECC is enabled. NVIDIA did issue a security notice based off of the GPU hammer work. I know this is an slide over here, but if you Google, you'll be able to find it. So with that, I'd like to conclude real quick, right? I mean, so DRAM is vulnerable, right? Scaling makes data disturbance errors worse. We've dealt with RowHammer for a decade now. We've dealt with RowPress for a couple of years. But guess what? There are more modalities, modes of data disturbance, right? This year at ISCA, column disturbance was introduced. What's next, right? It's a technology that is going to fail. It has modes, and more modalities of DDEs are going to come through. So we need an efficient mitigation approach for this, right? Interestingly, what we do desire is mitigations that generalize across different DDE modes. We've been able to take RowPress and convert it into a RowHammer problem. Column disturbance is completely different, right? With column disturbance, frequently accessing a column is causing bit flips in neighboring columns. That's something that neither PRAC nor Mint or Pride actually address because we're tracking rows rather than columns. We should be thinking about efficient mechanisms to address these problems, right? And of course, as we're looking at solutions to address this problem, let's take a security first principled approach that scales not only to today, but to the future. All right, with that, I would like to end my talk, and I'll be happy to take any questions. Exactly 30 minutes.
Are there any questions? I have a question.
Yes.
How much longer do you think DRAM technology can keep up with this, so we can scale further? RowHammer threshold will go down, maybe 100, maybe lower. Is it not time to maybe start thinking about other technologies? And on what time frame do you think that is reasonable, or are we going to stick with DRAM for the foreseeable future? Repeat the question.
The question that has been asked is, how much longer are we going to keep with DRAM technology, right? At what point are we going to change to a different technology, right? Is that a good summary of what you have asked for, right? I mean, so there are other technologies that are out there, right? But each of them has issues, right? I mean, there's flash out there, but it has issues as well. There's I think once those technologies that the issues with them are resolved, right? I mean, and you're able to bring them into the mainstream, I think you'll be able to use them, right? I mean, but now DRAM is there; it's a cheap commodity, right? There are capacity issues with it, right? I mean, the other technologies, they have endurance issues with them. There are bandwidth issues with them, right? Their writes take much longer compared to reads. So I think once those are resolved and they are able to compete and be as good as DRAM, yes, we'll be able to address it, right? I mean, the timeline of that, I'm not the DRAM expert or the memory DRAM technology expert. So when those are ready, I'm sure they'll be able to come, right? But for now, DRAM is here. It's to stay, right? So, yeah.
So maybe as follow-up, so you think, you say that PRAC, I guess, was designed for lower threshold, like towards 100, as you shown in the slide. You would say we do need PRAC solutions because, for example, min 50% that would keep up with more 1000s.
Okay. So that's a good question, right? Was PRAC designed for ultra-low RowHammer thresholds? PRAC was designed to keep up with the thresholds of what we have today, right? And it's supposed to be a principled framework to do so, right? And are DRAM technologies going to have ultra-low RowHammer thresholds of 100? We don't know, right? I mean, DRAM vendors are not going to be sharing this with us, right? But it's good to know that there is a technology, such as PRAC, that can cope and deal with ultra-low RowHammer thresholds of the future. But PRAC does have issues. The jury's still out, because to enable PRAC, you have to change the DRAM timing parameters. And those DRAM parameters have increased latency, right? The jury's still out whether or not you have performance overheads or not. In those situations, right, I mean, solutions like Pride and Mint will not have those 10% slowdowns that some people have talked about. But the jury's still out. Can't say that PRAC actually has that overhead unless we see that part. So we've got PRAC out there. It is an approach. It's a principled approach, right? DRAM technologies are going to be adopting it, as we've seen, right? But we need to make sure that that PRAC technology does support other modes of data disturbance errors.
Questions? All right, let's thank the speaker.
Thank you very much.